Hey, what is up you guys? It's me, Mikael, back with another video. Today we're going to talk about the Thevenin theorem. But before we start, make sure you go click that subscribe button, hit that bell icon so you can receive notifications from our channel. So, without any further ado, let's get started!
Thevenin's theorem states that any linear circuit containing several voltages and resistances can be replaced by just one single voltage in series with a single resistance connected across the load. In other words, it is possible to simplify any electrical circuit, no matter how complex, to an equivalent two-terminal circuit with just a single constant voltage source in series with a resistance connected to a load as shown.
Thevenin's theorem is especially useful in the circuit analysis of power or battery systems and other interconnected resistive circuits where it will have an effect on the adjoining part of the circuit. One of the benefits or importance of the Thevenin theorem is to avoid long and repeating of process between finding equivalent resistance, voltage, or current in complex circuits when one resistor's value is changed.
ML muna ako ah. Matagal to.
First step is to remove the R load and replace it with an open circuit.
Masyado kang mahaba.
First step is to remove the R load and replace it with an open circuit. And we will name these nodes A and B. Important note, since it is an open circuit, no current, energy, or anything will pass through these paths.
Now, notice here that R2 and the ones R load have the same nodes, A and B. So meaning they have the same potential difference or Thevenin voltage. But we will get onto that later on. To get the Thevenin resistance, we find the overall resistance or equivalent resistance of the circuit. If you notice, if we disregard the open circuits here, R1 and R2 are connected in series. So to find their equivalent resistance, you just add their resistance. And there you have it. 550 ohms is our Thevenin resistance.
Next, we need to find our Thevenin voltage. So Thevenin voltage is equal to the voltage across the R load. And we said earlier that the R load is equal to R2. So all we have to do is find the voltage across R2. Since we already know and have our equivalent resistance, also known as the Thevenin voltage, first we need to find the current throughout the circuit. The formula in finding the current is voltage divided by equivalent resistance. So 12 divided by 550 ohms is equal to 0.218 amperes.
Next, to find the voltage or Thevenin voltage, the formula is number of ohms of the resistor multiplied by the equivalent current. And since the circuit is a series circuit, their current is the same throughout the circuit. And so 0.218 amps multiplied by R2's resistance, or 330 ohms, we will get 7.2 voltage, and that right there is our Thevenin voltage. We will get 7.2 volts, and that right there is our Thevenin voltage.
We can stop there, but to truly understand why the Thevenin theorem is important, we can reconstruct the circuit. So now, we can add any R load or any resistor without going through the struggle of repeating the whole process of computing any needed values in the circuit. So let's add the R load here, and since it's connected in series with the Thevenin resistance, we can just add both of their resistance to get 1550 ohms. Divide that by 12 volts and you will get 0.0077 amperes. And since they are connected in series, that means all their currents are the same.
And there you go. That's the Thevenin theorem. Now, here's a short summary about our lesson today.
First, remove the R load resistor or the component concerned. Second, find the RS by shorting all voltage sources or by open circuiting all the current sources. Third, find the VS by the usual circuit analysis methods. And lastly, find the current flowing through the load resistor.
So, that's our lesson for today, the Thevenin theorem. I hope you learned something. Thank you.